All right, the next concept I'll be covering is Faraday's Law. Now, I got this definition from Khan Academy because I think it does a good job at summarizing in a more condensed way, but as we explore the equation more on a more conceptual level, it will make much more sense. So, Faraday's law, basically, I'm going to read right off, relates the rate of change of magnetic flux through a loop to the magnitude of the electromotive force induced in the loop. Basically, what this is saying is that if I change my magnetic flux, then I will also have a change or an induced electromotive force. So here I have written the equation where we have negative n times the change in electric flux over the change in time. So over this, this negative sign actually comes from Lenz's law, which you will also learn. So I've just written out what each of these variables stands for anybody that has never seen this before. So N is the number of turns. This is our flux, which is equal to the magnetic field times the area. And so then B here, I wrote out as well because some people, that's not a common term, such as like A. So B is the external magnetic field. So external B field, mean external magnetic field. And then the A is the area of the coil or whatever you are using. So as I go through these examples, I'm basically going to focus on one thing, and we're going to talk about how if we change different things, what will happen. So I will be explaining this concept by showing a coil moving across a sheet with a magnetic field. And these dots here, just to clarify, means that the magnetic field is away from you. So it's like pointing in. So it's like, if I was looking at it, it would be like out. So here I have my coil. And this is a uniform magnetic field. And I want you to think about what's happening when the coil is just sitting here. So to remind you of our equation is so here, basically, what we think about is what is changing, right? So, is my magnetic flux changing? Well, then we think about, well, what does that depend on? Well, that depends on my magnetic field in my area. So over here, has my magnetic field changed? I would say no. So no. Has my area changed? Has the area inside this changed? That it's enclosing? No, it hasn't. Okay, so moving on, we determined that the magnetic field's not changing, the area's not changing, so then the flux must not be changing. So then is our number of turns going to change? And number of turns for, to explain this to anybody, would be like if I had this box, my number of turns would be like the current flowing through it, basically, and how many times that goes around. All right, so now here, my coil is actually moving across the magnetic field here. So now I want to ask myself, is it now changing? So I look here and I see that my change in electric flux will equal my magnetic field times my area. My magnetic field is not changing, right? Nothing is changing inside this box. But what is changing is the amount of magnetic field that my coil is covering, right? Before I only had about 2 rows, now I have 4 rows of my magnetic field. So the area of my coil has not changed, right? The box is still the same, but what has changed is the amount of magnetic field inside it. So if my B increases, but my area is the same, what do we know about our change in magnetic flux? In electric flux, sorry. We understand that that must go up as well, right? So From this, we've learned that if we move this to the right, we actually have an increase in electric flux, which will actually make a current begin to flow in this coil, which is pretty cool.